Hello, everyone. Today it's my pleasure to introduce Arman, who's going to talk about some research he has done in the past 2 years about the Sudoku. I think I already asked some of you whether you play Sudoku. So after the talk, we will also have a user study so that not only you are going to learn what he has researched in the past, you can actually try it out. In his spare time, he like piano, soccer, and spending time with his family. Welcome, Aman.
Before I begin, I just want to thank you all for coming here, and I really appreciate you attending and listening to my talk. So 2 years ago, my pati, which means grandmother in Tamil, visited from India. And when she came, I learned that she loved to solve Sudoku puzzles. One day, she looked a little bit frustrated when she was solving her daily puzzle, and I went up to her and asked her, Pati, why do you look so frustrated? And then she asked me the question you see here. Why can I solve diabolical level Sudoku puzzles on one Sudoku website, but not easy puzzles on another Sudoku website? I approached this question with two distinct approaches to solving Sudoku puzzles. The first focuses on how a computer would solve a Sudoku puzzle, and the second is more human-oriented and focuses on how a human would solve a Sudoku puzzle. From these two methods, I derive two metrics that each characterize Sudoku difficulty. With these two metrics, I build a universal classification of Sudoku difficulty, which allows me to compare difficulty across the Sudoku websites. Then I share my results and observations, and finally I hope to conduct a user study. For those of you who have not solved Sudoku before, Sudoku is a 9 by 9 grid made up of smaller 3 by 3 grids. The goal is to fill the cells with the digits 1 through 9 such that each row, column, and 3 by 3 box contains each digit exactly once. Just a quick note about the notation I'll be using for a cell moving forward. A cell XY has where X represents the row number and Y represents the column number. The recommended way to begin solving a Sudoku puzzle is to compute the candidates. The candidates are the possible digits that can fill a cell. And to compute the candidates, you look at the row, column, and 3 by 3 box that a cell is in to see which candidates are not there. So if we look at, for example, cell 1, comma 1, if we look at row 1, column 1, in the top left 3 by 3 box, we see the only digit that does not appear are the digits 6 and 9. Another important construct in solving Sudoku puzzles is a contradiction. A contradiction is when a cell has no candidates, which is not possible. This means that the solver made a mistake when solving the puzzle and should go back to look for the mistake. The first method that I'll be introducing, which is a more computational an approach, is the encoding of a Sudoku puzzle into a satisfiability problem. A Boolean satisfiability problem is a formula of expressions, or clauses, and each clause is a disjunction of Boolean variables, or literals. The goal is to assign each literal a true or false value such that the entire formula is true. Each Sudoku puzzle has a unique SAT or satisfiability or SAT formulation, and we can use satisfiability problem solvers to solve the SAT formulation. When converting a Sudoku puzzle into its corresponding SAT instance, each candidate in the Sudoku puzzle maps to one literal. For example, if we look at cell 1, comma 1 with the literals with the candidates 6 and 9, there will be two literals for this cell, for the digit 6 and for the digit 9. If the digit 6 is assigned true, then 6 fills that cell. If the digit 9 is assigned true, then 9 fills that cell. But both 6 and 9 cannot be assigned true. It has to be either one. To actually create the SAT formulation of a Sudoku puzzle, we have to create clauses for the four constraints. The first constraint, the cell, states that each cell must contain exactly one digit. The row, column, and box constraints state that each row, column, and box must contain each digit exactly once. For the four constraints, there are two types of clauses. The first is an at least one clause. The at least one clause for a cell states that each cell must have at least one digit, and for the row, column, and box states that each must contain every digit at least once. The at least one clause example I have shown here states that for row 1, the digit 6 must appear in at least one of the empty cells. The at most one clause for a cell states that each cell must contain at most one digit. It does this by creating pairwise relationships between pairs of candidates in each cell to state that if this candidate goes into cell, then this candidate cannot go into cell. The at most one clause example I have given here states that for cell 1, 1, if 6 fills that cell, then 9 cannot go in that cell, and vice versa. A quick note about the length of clauses. A length of a clause is the number of literals which that clause contains. In a SAT formulation for a Sudoku puzzle, clauses can have lengths 1 through 9. So the length of the at least one clause we see here is length 4, and the at most one clause is length 2. Since at most one clauses creates pairwise relationships between candidates, all at most one clauses have a length of 2. The metric derived from this method is called clause length distribution. A clause length distribution is exactly what it sounds like. It is a distribution of clause lengths from a SAT formulation of a Sudoku puzzle. Clause length distribution has 3 categories. Short clauses counts the total number of clauses have lengths 1 and 2, and similarly for medium clauses and long clauses. Since clause length distribution is a distribution, we use the percentage of short clauses to represent clause length distribution as a single value. We choose percentage of short clauses since it has the largest variability from any of the 3 categories and is most likely to have predictive power of Sudoku difficulty. Please note that, as stated in the previous slide, all at most one clauses have a length of 2, so we do not consider them in our distribution as to not skew towards a length of 2. Our second method, which is more human-oriented, focuses on simulating human solvers. However, before I introduce the method, I would like to talk about Sudoku strategies. Sudoku strategies are logic techniques that people use to solve Sudoku puzzles. Most Sudoku strategies revolve around some kind of pattern recognition. There are tens of such Sudoku strategies, however, I have chosen 4. These 4 range from beginner to intermediate and allow me to simulate early Sudoku practitioners. The first of these 4 strategies is naked singles. Naked singles states that for a cell, if that cell has one candidate, it must fill that cell. I won't be going over the other 3 strategies in detail now. However, I will explain them in the user study. These 4 strategies can solve some puzzles on their own. However, it cannot solve the harder puzzles. So when the human encounters a puzzle they cannot solve with the human strategies alone, they have to use trial and error, or some kind of guessing. And the guessing adaptation for Sudoku is called Nishio. In Nishio, when making a guess, the human first has to choose a cell to guess in, and then the candidate that they will guess in that cell. The choosing of the cell is variable ordering, and the choosing of the candidate is value ordering. Once the human makes a guess, they can use the Sudoku strategies to continue to advance the puzzle. Once the Sudoku strategies cannot make any more progress, there are 3 possible situations the solver could face. 1, the puzzle is solved and there's no action needed. 2, there's a contradiction in the puzzle, which, if you remember, means a cell has no candidates. This means that the candidate we have assumed is the candidate that we guessed originally was wrong, and we can remove that as a candidate. We can then use this additional information to use the Sudoku strategies to continue solving the puzzle. The final situation that you could face is that the puzzle is not solved and there's no contradiction in the puzzle. This means another guess is needed. So you go back to step 1 and choose another cell and make another guess. The metric derived from this method is called Nishio human cycles. But before I talk how exactly this metric is computed, this is an outline of the algorithm I use to simulate human solvers. The variable and value ordering are randomized to allow to simulate beginner Sudoku solvers. When I was observing my grandmother solve her daily Sudoku puzzles, whenever she would make a guess, it would not be calculated at all, and she would make random guesses. So to simulate beginner Sudoku solvers, I randomize the value ordering and variable ordering. Once you make the random guess, the solver applies the 4 strategies repeatedly. So once, and in this order. So once X-wing has been applied, the solver goes back up and applies naked singles. The application of the 4 strategies once is 1 cycle. Once the solver finishes applying X-wing and goes back up to apply naked singles, a new cycle starts. So how exactly is Nishio human cycles computed? Well, we count the solver counts the total number of cycles needed to solve the puzzle. And the Nishio human cycles value for a single puzzle is the mean number of cycles needed to solve the puzzle over 50 solves. This allows us to simulate 50 random beginner Sudoku practitioners. Please note, because we randomize the variable and value ordering, the number of cycles needed to solve the puzzle will not be the same for each solve. Before I move on, I'd like to introduce the data set we use for our experiments. It is a 1,320 puzzle data set taken from 5 websites. Each website has a different number of difficulty levels. So for example, New York Times has easy, medium, and hard. The remaining 4 Sudoku websites have 4, 5, or even 6 difficulty levels. For my dataset, I've taken a total of 60 puzzles from each difficulty level in each website. Now we need to evaluate how well our metrics are at characterizing Sudoku difficulty. To do this, we ask the question, how well do these metrics correlate with the difficulty levels in each website? To answer this question, I calculate a Spearman's correlation coefficient. This returns a number between -1 and 1, with 0 being no correlation, between each of the metrics and the difficulty levels in each website. Now, there are multiple takeaways from this table. The first is that the clause length distribution has a high negative correlation. This means that the shorter number of clauses in a Sudoku puzzle SAT formulation, the easier the puzzle. The second is that Nishio human cycles has high positive correlation, which means the larger number of Nishio human cycles, the harder the puzzle. Finally, we can see that Nishio human cycles has a consistently higher correlation than clause length distribution. Now you may be wondering, well, extreme Sudoku has a near zero correlation for both metrics. And yes, this is true. Extreme Sudoku is an anomaly. We will address this in a future slide. Now that we've evaluated our metrics, we want to compare the difficulty levels across the websites. To do this, we can create a universal classification that is able to classify entire difficulty levels and individual puzzles. Now, this classification is built on Nishio human cycles, since as we saw, it's better correlated with the difficulty levels than clause length distribution is. So to create this universal classification, we consider the entire Sudoku puzzle dataset, ignoring the difficulty levels that each puzzle is from and the website that each puzzle is from. Then we run a univariate binning algorithm on that entire data set that bins the Sudoku puzzles into some number of bins and defines a range for each bin. We have 2 choices to make when running the binning algorithm. The first is the number of bins, and the second is the binning strategy. For the number of bins, I've chosen 3, since that's the minimum number of difficulty levels we see in a website. For the binning strategy, there are 2 choices. Either equal bin count, which prioritizes putting an equal number of data points in each bin, and the second is equal bin width, which makes each bin an equal width. Equal bin count is preferred for distributions that have moderate to great skewness. Over here to the right, we see a histogram which illustrates the distribution of puzzles of the puzzle dataset based on Nishio human cycles. Each bar has a width of 1 cycle and counts the number of puzzles whose Nishio human cycles value falls in that range. Running the binning algorithm gives us three categories. The first, universal easy. Second, universal medium. And the final one, which we call universal hard. We use these 3 categories to map difficulties level 2 in order to compare the difficulty across the websites. Here we see the universal classification. We have our 3 universal categories going horizontally with the ranges defined on the left. The mean number of Nishio human cycles across the difficulty level is shown in blue, and the median is shown in orange. So if we take New York Times Easy, for example, New York Times Easy has 60 puzzles. We compute the mean Nisho human cycles over the 60 puzzles and then map that in blue, which is, the value for that is 1.58. The median across the 60 puzzles is also 1.58. Hence, why you don't see the orange dot. For universal medium, the mean Nisho human cycles is 6.74 and the median is 5.32. For New York Times Hard, the mean Nisho human cycles is 13.18 and the median is 10. For 4 out of the 5 difficulty levels, we see nice progression with the difficulty levels from each site and the universal categories. However, as we saw before, Extreme Sudoku seems to be anomalous, with all 5 difficulty levels classified as universal hard with the mean Nisho human cycles. Upon this finding, I actually contacted the puzzle makers for Extreme Sudoku, and right now I don't have enough time to go into what they said in detail, but they did confirm our findings, stating that all 5 difficulty levels are around the same difficulty, and all 5 of them are hard. Before I take any questions, I'd like to summarize the key contributions of this study. The first is 2 Sudoku solving methods, which can both solve every Sudoku puzzle. From these 2 methods, we derive 2 metrics that allow us to characterize Sudoku difficulty in Sudoku websites. I hope to make the Sudoku puzzle dataset public in the future, and from my knowledge, it would be the largest public Sudoku dataset. And finally, I create a universal classification of Sudoku difficulty, which allows us to compare Sudoku difficulty across websites. Thank you for listening.
How did you connect the puzzle dataset?
Sorry?
How did you collect all the dataset?
Oh, so basically, so the websites, they post one every day. So so I had to sit down every day and take a picture of each puzzle and then like save it in and save it.
So this is like a multi-year effort.
Yes.
I have a question. In the Nishio and the human cycles, right?
Yes.
So like choosing random at first.
Yes.
I personally, maybe this is a subject of your study. I think I tried to find naked singles first.
Yes.
And I don't do random first.
Yeah, so that's just the algorithm that allows us to collect the Nishio human cycles metric. In the user study, I will give a proposed algorithm that I would I'll share my proposed algorithm where you actually apply the strategies first, and then when you're sure they can't advance the puzzle anymore, only then do you choose a cell using Nishio. And
Right.
Yes.
Did you simulate that as like another metric?
Yes, we did simulate that, and I'll share those in the user study, that kind of findings.
Have you shared your work with your grandma and help her select the right Sudoku puzzle to work with?
So actually, I told her, so the extreme Sudoku, which like all the difficulty puzzles levels were hard, that's what actually was stumping her, because she wasn't able to solve the easy level in extreme Sudoku, because it's classified as universal hard. And so I told her, no, don't go to that site anymore, it's a bad site. If there's no more questions, we can take a break before, yeah, I think we're
I
finished.
have one more question.
Yes.
So I think you explained a little bit on why you started to work on this project, right? But do you have more motivation? Like, is that the story you shared at the beginning is the main motivation? Your grandma kind of found it puzzling that an easy puzzle on a website is more difficult than the other?
Yeah, I think that's because my grandmother, she was solving for like the last 40 years. She would do the puzzle every day in the newspaper, and now because they started posting them online, it was easier for her to access them. And I didn't really like seeing my grandmother being so frustrated. I wanted to enjoy solving Sudoku puzzles. And so when she asked me that question, I mean, it really motivated me to answer it.
Personalized, like more human grading of Sudoku.
Yeah.
Okay.
And also, I've done a lot of research into previous efforts in characterizing Sudoku difficulty, and there's not like one big way to classify it and compare difficulties across websites. So it's still like an open field of research.
Very nice. Very nice.
How do you do with the puzzles on your own? Do you do really good?
Before, like 2 years ago, when my grandmother visited, I was really bad at it. But like since then, I've actually doing the research. I've actually gotten pretty good at it. Yeah. Method I use, I'll be showing that in
The
the
user?
user study. Yeah.
Okay.
So that's another incentive. User study. Okay. Any other question? Yeah.
You
Okay.
want to build like a website categorizing all of the Sudoku puzzles of the day, which is the most difficult versus easier? Like, do you want to do any categorization?
It's actually
Release
so funny
that?
you ask. I'm in the middle of building a website right now,
Okay.
which I hope to post like every day from these 5 websites, classifying each of the difficulty levels from the puzzle.
Or maybe make an app, right?
Or an app, yeah.
Very nice. Okay. Yeah, let us know when it's available. Okay. Yeah, thanks so much, Anna. Excellent.
Thank you.
Thank you guys so much for coming.
So we will have a user study in Holy, so the room with the window in a few minutes. Yeah, around the 4. But I think the user study itself, how long does it take?
It'll be maybe half an hour.
Okay, yeah, so we'll start at 4. So please grab some chocolate and then hope to see you in Holy.
Grandma was like hardcore into Sudoku also.